Hi. This video describes how the NES sound engine used in such games as D-Pad Hero and D-Pad Hero 2 was ported to the Game Boy. The video is based on the article linked in the description. The original NES sound engine has largely remained unchanged the last 20 years. For this project, in addition to getting familiar with the Game Boy hardware, I wanted to take the opportunity to apply some learnings from the early design choices and consider how the engine could be improved, chiefly by removing unnecessary complexity, adhering to the so-called Yagni principle. You ain't gonna need it. The initial objective and key result of this project was to take the Super Mario Land World 1 remix for NES, linked in the description, and make it sound good on Game Boy. Features were implemented on a strict need-to-have basis. The Game Boy engine doesn't yet have full feature parity with the NES engine. For example, layering sound effects on top of the music, a feature needed for games, is not yet implemented. If you just want to listen to the final result, check out the link in the description. Part 1. NES vs Game Boy sound hardware. Both NES and Game Boy have two pulse wave channels featuring 16 volume levels, 3 duty cycles, and fine-tunable pitch. The pulse channels have hardware support for volume envelopes, length timers and pitch sweep. In the sound engine, I've chosen to implement those features in software instead, as it gives more flexibility, and there isn't too much overhead involved in doing so. Both NES and Game Boy have a noise channel with 16 volume levels, supporting static and regular, so-called tinny, noise, and comparably coarse grain pitch. The NES has a triangle wave channel with only 2 volume levels, on and off, and fine-tunable pitch. The NES has a DPCM, that's Delta Pulse Code Modulation, sample channel with programmable sample data. This channel does not have any volume control. It's up to the programmer to define soft or loud sample data, and it only supports a coarse grained set of frequencies, whole notes. It's typically used for drums, for example in Super Mario Bros. 3, and bass, for example in Gremlins 2 and Journey to Silius. The Game Boy has a 4-bit sample channel, commonly referred to as the wave channel, with programmable sample data. It has 4 volume levels, and fine-tunable pitch. The waveform can be programmed to be a pulse, triangle, sawtooth, sine, or custom shape. The Game Boy supports panning each channel. The sound engine doesn't support panning yet, but this feature could be implemented with relatively little effort. Part 2. Song data. The sound engine consumes song data that can most easily be created by converting XM, that is, extended module files using the tool XM2NES. The XM format was first introduced by the program Fast Tracker 2. For the Game Boy version, I modified XM2NES slightly to create XM2GB. The sound capabilities of NES and Game Boy are so similar that not many adjustments had to be made. Also, the song format is mostly hardware agnostic, which makes it easy to adapt to any system that has sound channels with programmable pitch and volume. The philosophy is that the format and core engine can use a relatively high level of precision in software, and then the engine state can be downscaled as necessary when the time comes to materialize the sound on the hardware. XM files. An XM contains a set of patterns to be played in a defined order. Patterns can be repeated as necessary, to save space and avoid copy and paste of identical sections of a song, particularly useful when a song has a verse-chorus structure. Each pattern consists of rows, typically 64 per pattern. Each column defines notes and commands and effects for one channel. The first column is channel 0, the second column is channel 1, and so on. The XM also contains definitions of instruments. Each instrument has a waveform, 8 or 16-bit sample data, associated with it. An instrument can have additional settings, such as a volume envelope, panning, and default vibrato. In the conversion process, the XM instruments are mapped to instrument definitions in the sound engine's own format, described later. XM2GB. The XM2GB command line utility parses an XM file, analyzes it and generates its own internal, optimized representation, and outputs an assembly source file. The source file is compatible with the RGBDS assembler. The converted data together with the instrument definitions form a complete song that can be consumed by the sound engine. Song format. The song data consists of a header, an order table, an instrument table, with volume envelope definitions, and a pattern table. The song header. The first part of the header describes the song's tracks and their initial speed. Think of a track as a virtual channel. The term, track, is used to avoid confusion with the actual hardware sound channels of the target system. XM2GB maps the channels of the XM, 0, 1, 2, and 3, 1-to-1 to tracks in the output. Additional channels of the XM are ignored. The first byte of each 2-byte pair is the starting offset of the track within the order table. If a track is not used at all, this field is set to the hexadecimal value FF. The second byte is the initial speed of the track, in number of ticks, aka frames, per row. Bigger values are slower, and speed 1 is the fastest. In practice, all tracks in songs converted by XM2GB have the same speed, because there is no way to control the speed of individual channels in an XM. The sound engine runs its processing once per frame. This is referred to as a tick. On the Game Boy, that's approximately 59.73 times per second. If you were to write the song data by hand, you could use variable speed per track, but it seems there's not much to gain from it. The song format could easily be modified to only store a single initial speed, and the sound engine could apply it to all tracks. The last part of the header are the pointers to the instrument table and pattern table. The song header does not have a version indicator. XM2GB includes a comment in the generated assembly file that says which version was used. For each new Game Boy project, I make a full copy of the sound engine, and then adjust the implementation as necessary whenever I make a breaking change to the song format. Order table. The order table follows immediately after the header. It's an array of pattern indices for each track. The order table can also contain commands to loop a part of the order, or jump to a given offset, typically used for looping a song back to the beginning. Order commands. The NES sound engine supports the following order commands. The Game Boy engine so far only implements the FE command, go to, and it does so only partially. It cheats by just restarting the whole program. The other commands haven't been needed. In practice, there aren't many cases where looping a part of the order yields any benefit. Given the following plain order, it could be written as the following loop. Both versions occupy 6 bytes of storage. The loop variant is more complex to execute because it requires state management in the sound engine. Similarly, I've found it to be rare that all the notes in patterns of a section of the order can be usefully transposed without needing any other changes to the pattern data. Loops and transposes add complexity to the song converter to detect common subsequences, etc., and they add complexity to the sound engine for no compelling reason, so these features could safely be scrapped. Instrument table. The instrument table is an array of instruments, each 8 bytes in size. The instruments are not produced by the XM2GB tool itself, the programmer has to define them by hand. When you invoke XM2GB, you pass it the path to an instruments mapping file that says how the instruments in the XM should be mapped to instruments in the target song. Instruments mapping file. The contents of an instruments mapping file can look like the following. Source is the index of the XM instrument. Target is the index of the instrument it should be mapped to in the output. Transpose defines a signed delta that should be added to each note to produce the final value in the output pattern data. To get started on a new song project, I usually make a copy of an entire folder of a previous song, including the XM file, the song's assembly file, and instruments mapping file, and then I zap the song's patterns. Then I adjust the instruments mapping and instruments data as needed. Instrument structure. All 4 tracks use the same instrument format. Here is an excerpt from an instrument table where instruments 0, 1, and 2 all share the same volume envelope. Default effect and parameter. The supported effects are described in a later section. Setting a default effect on the instrument can save space and avoid redundancy and repetitiveness in the pattern data. The effect will be re-triggered each time a note is triggered. In the NES sound engine, byte 2 of the instrument could be used to define an effect delay. This would cause the default effect, typically vibrato, to be delayed by a number of ticks. In practice, I found that when I have a need to delay an effect, it's better not to set a default effect on the instrument, but instead apply the effect in the pattern data on a per note basis. This gives more flexibility and removes some complexity in the sound engine, at the expense of slightly larger pattern data size. One typical default effect I use for instruments played on the wave channel, triangle channel on NES, is slide down, to simulate a bass drum or snare drum. Duty cycle settings. For an instrument that will be played on a pulse channel, the duty cycle settings byte defines the initial duty cycle, 2 bits, the final duty cycle, 2 bits, and the number of ticks, also 2 bits, before changing from the initial to the final duty cycle. If the delay field is 0, the initial duty cycle field is ignored. As an example, the hexadecimal value 2C means, for the first 3 ticks of playing the note, use duty cycle 0, 12.5%, then switch to duty cycle 2, 50%. I first became aware of this duty cycle effect when studying the music in Sunsoft games on the NES, such as Gremlins 2. Rapidly changing the duty cycle produces an attack that can almost make it sound like two instruments are played at once. It works particularly well with duty cycles 0 and 2 because they have the biggest contrast, going from coarse to smooth and vice versa. In the NES sound engine, the number of ticks before changing the duty cycle is a 4-bit value, giving a maximum delay of 15 ticks. In practice, I found that the values 2 and 3 work best. The effect loses some of its punch if the delay is longer than that. To support those cases where the composer wants to change the duty cycle at an arbitrary time, I added a dedicated effect that can be applied to any row in the pattern. Noise channel LFSR width. For an instrument that will be played on the noise channel, the duty cycle settings byte holds the LFSR width in bit 7. 1 equals tinny noise. It can make the noise channel sound like a triangle instrument, or like metal, the most famous example being the Metal Man stage music in Mega Man 2. Volume envelopes. A volume envelope specifies the initial volume of the instrument, and how the volume should change over time. All 4 tracks use the same envelope format. Since each instrument has a pointer to a volume envelope, envelopes can be shared between instruments, and even between songs. Volume envelopes, like instruments, are not part of the output from XM2GB. You can define volume envelopes for instruments in the XM file itself, but they are ignored by XM2GB. The volume envelope format is very much inspired by the way volume envelopes are defined in Fast Tracker 2, a series of points that the engine will interpolate between, and the ability to sustain or loop the envelope from a given point. This can be used to model basic ADSR, attack, decay, sustain, and release envelopes, as well as more complex ones. The following is the most basic envelope definition. It defines an envelope that maintains a constant volume until the note is released, then fades out rather quickly. Hexadecimal F0 divided by 8 equals 30 ticks, approximately half a second. The initial volume is an 8-bit value. 255 is maximum volume and 0 is completely silent. The next bytes form a series of triplets, where the first byte is the delta, which is the amount to add to or subtract from the current volume each tick. The second byte is the target volume, 0 to 255. The third byte is how many ticks the volume should be sustained at the target volume before proceeding to the next point in the envelope. A value of 255, hexadecimal FF, means that the volume should be sustained forever or until the note is released. The release command will be described in a later section. When a delta value of hexadecimal FF is encountered, it signals the end of the envelope. The next byte determines whether the envelope processing should be halted completely. FF, the volume will remain at the current level, or looped from the given offset. In the NES sound engine, the delta uses an 8.8 fixed point representation, 1 byte integer part, 1 byte fraction. In practice, I found that using a 4.4 fixed point representation, 4-bit integer part, 4-bit fraction, gives sufficient precision. When composing a song, I initially rely on the basic, constant volume envelope, and change the track volume via pattern commands. When I get to the post-production stage, I introduce dedicated instruments and volume envelopes where it makes sense. The savings in storage space can be significant. Pattern table. The pattern table is an array of pointers to patterns. The order table contains indices of patterns in this table. The pattern table is shared between all tracks. Technically, it's possible to use the same pattern in more than one track. In practice, all tracks have their unique set of patterns, because pattern data is never exactly the same on different tracks. Why use single-track patterns and separate order tables per track, instead of multitrack patterns and a common order table, like in the original XM files? Because some tracks are often more regular, repetitive, and/or less busy than others. For example, the percussion and bass line, typically played on the noise channel and wave channel, compared to the lead, typically played on a pulse channel. By treating each track separately, we get the best opportunities for detecting unique patterns in each track, so that pattern data won't be repeated unnecessarily. Pattern data. The pattern data is an encoding of the notes, effects, commands, and rests that make up a pattern of n rows of one track. A pattern's data can look like the following. The first byte is the number of rows in the pattern, 64. The remaining bytes is a mix of row status bytes, notes, and effects and other commands. The storage consumed by patterns can vary greatly depending on how busy aka complex each pattern is. Row status byte. Typically, not every row of a pattern has a new note, effect, or command. To save space, At the start of every 8th row, the pattern data contains a byte that defines which of the upcoming 8 rows have some data defined for them. Rows that have a 0 bit in the status byte do not have any data. Rows that have a 1 bit in the status byte have some data. Notes. Notes are indexes into a period table. Value 0 is C2, value 1 is C#2, value 12 is C3, value 24 is C4, and value 71 is B7. Notes and effects and other commands. How the data for a row in the pattern is interpreted depends on the value of the next byte of pattern data. If the value is between C0 hex and CF hex inclusive, it's a set speed command. If the value is between D0 hex and DF hex inclusive, it's a set volume command. If the value is between E0 hex and EF hex inclusive, it's an effect, which can have a parameter. If the value is greater than or equal to F0 hex, it's an extended command, which can have a parameter. Otherwise, the value is a note, and it signals the end of data for this row. What's the difference between a command and an effect? They both change some state of the track, but commands are only processed on the first tick of a row, whereas effects are processed on all ticks. Zooming in on this pattern data. The first byte, row status, tells us that the next row has some data, but the subsequent 7 rows do not. Next, set the current instrument to be hexadecimal D. Next, set the current effect to be arpeggio, with a parameter of hexadecimal 59. Finally, play the note hexadecimal 1F, G4. Indeed, if we look at the pattern in Fast Tracker 2, we can recognize these 8 rows from the data. The note in Fast Tracker 2, C4, is different because of a transpose that is applied by the converter. Effect types. An effect type byte can be followed by a parameter byte, depending on the type of effect. Effects are processed on every tick. A new effect can only be set at tick 0 of a new row. Effects are described in more detail in a later section. Set speed command. The set speed command sets the speed to the value of the lower 4 bits of the command byte plus 1. The speed is applied to all tracks. For setting the speed to higher values than 16, an extended command must be used instead. We'll get back to this shortly. Set volume command. The set volume command sets the track's master volume to the value of the lower 4 bits of the command byte multiplied by 16. Extended command types. An extended command type byte can be followed by a parameter byte, depending on the type of command. Commands are only processed on tick 0 of a new row. In the NES sound engine, set speed and set volume are both extended commands that occupy 2 bytes. To reduce storage consumption, I introduced the more compact commands. Songs that use a swing, aka funky tempo, typically change the speed every even row of the pattern. By having the size of each command, the savings can be tremendous. Similar savings can be achieved for those cases where manual volume control is used instead of a volume envelope. Part 3. Sound engine architecture. Each tick, approximately 59.7 times per second, the sound engine performs the following steps for each track. Advance time by 1 tick. Update row, pattern, and order state appropriately. Process pattern data for new row, if a new row was reached. Process effect. Process volume envelope. And finally, render the track state to sound hardware registers. Then, we sit back and let the Game Boy hardware output sweet sounds until the next tick. Track data structure. In the NES sound engine, separate data structures are used to represent the state of each track stage. The NES sound channels are quite heterogeneous compared to the Game Boy. In particular, the DPCM channel is completely different from the other channels. For the Game Boy engine, since the hardware channels are all configured in a similar way, I opted to represent each track by a single structure that holds the state associated with all stages. The same processing is performed on all tracks. They all support the same effects and high-precision period values and volume envelopes. Track mapping. Tracks are mapped to hardware sound channels using a fixed mapping. The composer must adhere to this mapping when creating the song. Part 4. Effects processing. Slide up and down. The parameter to these effects is the amount, the rate, to add to or subtract from the period value each tick. A low rate produces a long slow slide. Note that the period table is not linear. The higher the frequency, the smaller the difference between one period value and the next item in the table. To maintain a similar rate of change in audible frequency, you'll want to use a higher rate when sliding from a low period value and a lower rate when sliding from a high period value. This graph shows the difference between the entries in the period table, starting with the difference between C#2 and C2, the lowest possible note, and ending with the difference between B7, the highest possible note, and A# 7. Portamento. The parameter to this effect is the amount, the rate, to add to, or subtract from, the period value each tick until the destination note's period value is reached. A low rate produces a long slow portamento. Vibrato. The parameter to this effect is a byte where the high 4 bits define the speed of the vibrato and the low 4 bits define the depth of the vibrato. A small speed value produces a slow vibrato. A large depth value produces a deep vibrato. Since the period table is not linear, the composer should usually be conservative with the depth when applying vibrato to a high note, or else the vibrato can sound very extreme, almost operatic. Bubble Man stage in Mega Man 2 is a good example. Of course, it's up to the composer to decide whether they want an exaggerated or moderate effect. Arpeggio. The parameter to this effect is a byte where the high 4 bits define the delta to add to the bass note on the 3rd and 4th tick, and the low 4 bits define the delta to add to the bass note on the 5th and 6th tick. On the 7th and 8th tick, the bass note is played again, and so on, producing a very rapid arpeggiated chord. A popular effect achieved with an arpeggio is to use a parameter of C0 hex to alternate quickly between 2 octaves of a note, producing a shrill sound. Cut note. The parameter to this effect is the number of ticks after which the note should be cut, which means setting the volume to 0. This produces a staccato effect. This is different from the release command, which expires the current sustained counter of the instrument's volume envelope. Part 5. Rendering the track state to sound hardware registers. Rendering the track state is the process of converting said state to values that are written to the sound hardware registers, according to the parameters and capabilities of the associated channel. Pulse channels. Duty cycle. The duty cycle bits are derived from the track square duty CTRL field that comes from the current instrument's definition. Volume. The pulse channels support 16 volume levels. The output volume is a verbatim copy of the upper 4 bits of the computed 8-bit volume of the track. One interesting quirk, and difference from the NES, is that the volume written to hardware register NRX2 only controls the initial volume of the channel when the channel is triggered. Unfortunately, since re-triggering the channel causes the channel to start playing its wave from the beginning, fading in and out the volume this way sounds janky. I figured there must be a way to lower the volume without re-triggering the channel. Just when I thought all hope was lost, an article from gbdev.gg8.se came to the rescue.
Zombie mode. The volume can be manually altered while a channel is playing by writing to NRX2. The only useful consistent behavior is using add mode with a period of 0 in order to increment the volume by 1. That is, write V8 hex to NRX2 to set the initial volume to V before triggering the channel, then write 8 to NRX2 to increment the volume as the sound plays. Repeat 15 times to decrement the volume by 1. This allows manual volume control on all units tested.
Sure enough, it works beautifully. To determine how many times the NRX2 register should be written to increment or decrement the volume, we need only subtract the previous tick's absolute volume from the current tick's absolute volume. Period. The pulse channel period is simply copied verbatim from the track period low and track period high fields to the corresponding hardware registers. When a note is played, without portamento effect, the high bit of the track period index field is set to signal that the channel should be triggered. This bit is copied to the high bit of the NRX4 register, then set to 0. Wave channel. Wave pattern RAM. So far only one hard-coded wave pattern is supported. It's written to wave pattern RAM when the program starts up. The NES sound engine supports defining a custom set of DPCM samples for each song. It would be nice to provide a similar capability in the Game Boy engine, so that different songs, or even a single song, could use different samples for their instruments. Volume. Unlike the pulse channels and the noise channel, the wave channel supports only 4 volume levels. The output volume is derived from the upper 2 bits of the computed 8-bit virtual volume of the track, according to this table. Period. The period of the wave channel works the same way as the pulse channels. Noise channel. Volume. The volume of this channel works the same way as the pulse channels. Period. The noise channel has a different way to define the frequency. It's derived from a 7-bit value instead of an 11-bit period value like the other 3 channels. I wrote a script that computes all the unique frequencies. Some 7-bit values produce identical frequencies. It turns out that there are 63 unique values. I ordered them from low frequency to high frequency, like the 11-bit period table, and duplicated the last value to get a table of size 64, so that it can be indexed by a 6-bit value. Now all that's needed to convert from the 11-bit period value to 6-bit index is to divide the period value by 32, which is quick to do with a few shift and rotate instructions. The noise channel supports effects like slide up and slide down and vibrato, but because the resolution of the output is lower than the other channels, the changes in audible frequency can appear more coarse and abrupt. Part 6. Implementation Notes. Implementation Strategy. The sound engine is a non-trivial program. It manages quite a lot of state. It reads and decodes order data and pattern data. It processes effects and volume envelopes. It translates the state into values that are written to the Game Boy sound hardware registers. How was I going to port the mature and battle-tested NES sound engine to a new unfamiliar platform in a reasonably effective way? Step 0. Getting started with Game Boy development. The very first step, before it's possible to even think about how to port the sound engine, was to find a tool chain and get a Hello World program up and running. Part 1 of the GBASM tutorial on gbdev.io was very useful. Installing RGBDS. Full disclosure, my MacBook is so old that it's challenging to compile RGBDS from source. I ended up running an Arch Linux image on AWS and installed RGBDS there. I used SCP to copy files between the development machine and my local system. Putting something on the screen. The Game Boy PPU, Picture Processing Unit, is very similar to the NES PPU. Nametables are the same. Tiles have a very similar format. Sprites have a very similar format. The concept of only being able to write to PPU memory, VRAM, during the vertical blanking interval is the same. My strategy was to learn a sufficient amount of assembly language to be able to port the basic NES routines for buffered VRAM and sprite memory, OAM, transfer. I relied, and still rely, heavily on RGBDS's language reference. There is a comprehensive disassembly of Tetris which I found to be an excellent resource for learning idiomatic Game Boy programming. Step 1. Getting to know the Game Boy sound hardware. Once I had a Hello World program running, I proceeded to write a small test program that produced sound on each of the 4 Game Boy sound channels in the simplest way, so that I could get familiar with the hardware registers and understand the channel's capabilities and differences. The pan docs were extremely useful. Step 2. Start processing the song data. Next, I started implementing the sequencer part of the sound engine, reading and decoding order data and pattern data. I focused on processing just the first track, since all tracks have the same layout and capabilities. Once the first track works, the others should work too. I relied heavily on the debugger in the same Boy emulator to verify that the engine's state was being updated as desired, stepping through instruction by instruction, and inspecting memory. The symbol file produced by the RGBDS assembler, which lists the addresses of all labels, was tremendously valuable. Same Boy's debugger uses a GDB-inspired text interface, which meant I could quickly get productive with it. Same Boy even reads RGBDS.sim files and shows the symbolic addresses. Step 3. Materialize some sound. Next, I implemented basic rendering of the first track to hardware, the first pulse wave channel, so that I could actually hear some output and didn't only have to rely on the debugger to check that I was on the right track, no pun intended. Step 4. Implement volume envelopes and effects. Next, I implemented volume envelope processing, and then effects processing. Since these are separate stages in the engine's pipeline, they could easily be commented out and in to make it easier to track down the source of bugs. I sometimes relied on multiplying the song speed by a factor, 8, in code to slow the song down considerably, so that I could more easily listen and understand precisely at which point something started to go wrong with the playback, pattern decoding, effect processing, or envelope processing. Step 5. Process all tracks and materialize them. Once I had the first track sounding okay enough, I expanded the processing to 2 tracks, then 3, then 4, adding the hardware rendering of each channel along the way. There is a separate procedure for rendering each channel. The Game Boy sound channels have similar, but also some distinct features. Here's a breakdown. Despite the similarities, I opted for creating a separate procedure for each channel without any code sharing. These procedures rarely change. I prefer them to be as simple and decoupled as possible. It's a relief to be able to write a few pieces of code that don't have to do any dynamic addressing. We'll get back to this topic. Sometimes, a little code duplication is fine. Step 6. Add simple visualization. Next, I implemented the visualization of the track's volume level, and the ability to turn each channel off and on with the D-pad, just to get some familiarity with processing input too. Step 7. Played at the Game Boy's strengths. Finally, I made some adjustments to the song, Super Mario Land World 1, to adapt it to the Game Boy. The original NES version used the DPCM channel for percussion. I ported the percussion to the noise channel on Game Boy. I made the wave channel, the bass line, a bit more bouncy, since the Game Boy wave channel comes through a lot better than the triangle channel on the NES, which has a very soft sound. Game Boy CPU impressions. Apparently, the Game Boy CPU is a mix between the Zilog Z80 and the Intel 8080. I couldn't tell because I'm not familiar with either of those processors. This is the first project where I've written assembly code for the Game Boy. Here are some thoughts on porting the code from the NES 6502 processor. Addressing. Warning, long rant ahead. 6502, aka yay, you can index stuff. The Game Boy CPU lacks an indexed addressing mode like the 6502. The 6502 has several indexed addressing modes, both direct and indirect. Indexed addressing modes are extremely useful when working with structs or arrays of structs, where each field has an offset from a base address. With this approach, we effectively achieve random access to any field of the struct without having to change the X register, for the whole duration of each loop iteration, track in this case. We don't have to care much about the layout of the struct, because accessing any field is free. If we reorder the fields or add or remove a field, the code for accessing the fields can remain unchanged. The assembler will recompute the offsets for us. In other words, this is an essential mechanism for writing compact and maintainable code, and on the 6502 I completely take it for granted. Game Boy CPU. AKA, indexing? Are you absolutely sure you want to do that? With the Game Boy CPU, it's only possible to load a value indirectly from, or to, the address in one of the 16-bit registers, BC, DE, or HL. There is no way to index the base address by either another register or a constant offset as part of the instruction encoding. I've never encountered a CPU that had this limitation. I found it to be incredibly tedious. Apart from the add HLR16 instruction, you cannot add a value directly to a 16-bit register. The other add instructions only support the 8-bit accumulator register as a target. So you'll have to move the low address register to A, add the offset to A, then copy the accumulator back to the low register. That's 3 instructions, 4 bytes, 4 cycles, just to advance HL to the next field. And the result is only guaranteed to be correct when HL plus offset cannot cross a page boundary. If the addition could cross a page boundary, we have to check the carry flag as well. 5 instructions, 7 bytes and at worst 8 cycles. To avoid the carry flag check, I make sure that the data structures are aligned so that they are guaranteed to be placed inside one page. An alternative approach is to load the offset, constant, into the BC or DE register, and then add that register to HL. That's only 2 instructions, but still 4 bytes and 5 cycles. Such a shame that there isn't an instruction to load an 8-bit constant into a 16-bit register, 0 or sign extending it. Also, normally I can't afford to clobber the BC or DE register, because those contain other data. Sure, we can preserve the register with push and pop. But that brings the instructions up to 6 bytes and 12 cycles. I can't bring myself to wasting precious resources like that. Auto increment and decrement of HL to the rescue, somewhat. The Game Boy CPU provides special forms of the LDHL instructions, where the HL register is auto-incremented or auto-decremented after the load or store. The sound engine relies heavily on these instructions to avoid additional pointer arithmetic. That's a lot more compact. But it relies on having perfect ordering of fields in the struct. Notice that in some places, INC-L is used to skip a field. That is still faster and more compact than having to perform an addition on L via A, as long as you only have to skip 3 to 4 bytes. Notice how we went from hardly having to care about field order at all on the 6502, to field order on the Game Boy CPU becoming the most important thing needed to achieve compact code with low cycle count. This can feel aggravating and conflicting, especially when the same struct is accessed in different ways from different parts of the code. The order I ended up with for the track struct was the result of several iterations. The guiding principle was that the code on the common hot path of the sound engine should be able to access consecutive fields, as much as possible. The downside of the auto-incrementing HL approach is that it's very easy to lose track of what field the HL register actually points to, especially when there are branches involved. My way to maintain just an inkling of sanity about this was to comment, on every line involving the HL and L registers, the name of the field being accessed, as seen in this snippet. Similarly, Below label definitions, I'd comment the name of the field that the HL register should point to upon entry, and then try to verify that all the branch points respected this. Still, I had some bugs that required focused debugging sessions, stepping through a lot of code blocks. Despite the diligent comments, I broke the engine a few times when removing and rearranging fields, even though I was careful to only do and verify such changes one at a time. Honestly, this walking up and down memory via HL ordeal feels uncannily similar to how a Turing machine is described.
More explicitly, a Turing machine consists of a head that can read and write symbols on the tape, and move the tape left and right one, and only one, cell at a time.
I totally sympathize with the head, and I've begun to think there is a special place in HL for pointers like these. Useful direct operations involving the HL register. The Game Boy CPU provides a few instructions that operate directly on the byte pointed to by HL. It's nice that data operations don't always have to go through the accumulator register. High RAM. The Game Boy CPU provides something similar to the 0 page on the 6502, where the high address byte is implied, FF hex. This is useful to shave one byte in one cycle off of the instruction. Swapping nibbles. The swap instruction swaps the low and high 4 bits of the register. In the sound engine, this was useful on a few occasions, since 4 bits are used to represent a channel's computed volume, but in the NRX2 hardware register they are stored in the upper 4 bits. Swapping is a lot more compact than having to perform 4 shift instructions. Instructions with surprising effects. The AND, or an XOR instruction set the carry flag to 0. This tricked me a few times, and will likely continue to do so. I was expecting the carry flag to be preserved from a previous instruction. Conditional read. It's nice that the read instruction can take a condition code. Aligning on a page boundary. I was not able to get the DS align directive in RGBDS to work with alignment greater than 16, so I wrote this macro that pads to the next page. Conclusion. The Game Boy CPU has a crippling lack of indexed addressing modes, but the Game Boy sound chip is cool. The programmable wave channel gives a lot of possibilities. There you have it. Thanks for watching. For more videos, make sure to like and subscribe, and leave a comment. Until next time, take care.